Good morning or good afternoon, wherever you happen to be. This is Neil Paulhemus, and I'm about to start in on the second part of the webinar that we started about a month ago, talking about the use of multivariate methods in using Statgraphics Centurion. As always, I'm going to be analyzing a real data set and hopefully demonstrating some of the capabilities of Statgraphics when it comes to analyzing multivariate data. You are invited during the course of this presentation to send us messages using the GoToMeeting message facility. And after I talk, finish my formal talk, I'll be happy to entertain whatever questions you submitted during the seminar. Okay, let's get started. If you were with us about 5 weeks or so ago, you'll know that I defined multivariate statistical methods as the simultaneous observation and analysis of more than one response variable. And there are a number of uses of multivariate statistical methods, and I listed 5 from the book by Johnson and Wishern on applied multivariate statistical methods. The first use, the one we talked about primarily during the last webinar, was data reduction or structural simplification. Methods like principal component analysis and factor analysis that were helpful in basically reducing the dimensionality of the problem. When you had lots and lots of variables, reducing that set of variables to 2 or perhaps 3 linear combinations that contained most of the information that all of the variables you were looking at contained. That made it possible for us to display the results in a way that was much easier to understand. The second primary use, and the one we're going to be talking about today during today's webinar, is sorting and grouping. Taking observations that are defined by multiple variables and putting them into groups. Now, it's going to involve things like cluster analysis, discriminant analysis, neural networks, those sorts of procedures. Very, very useful, very, very widely used, particularly in the areas of data mining. Other uses, you can read them here: investigation of the dependence amongst variables, prediction, hypothesis testing, and so forth, are sort of sprinkled in throughout the webinar as secondary goals, perhaps, of what we're trying to do with these statistical methods. Now, the data set I'm going to be looking at today has to do with the demographics of the 50 states that comprise the United States of America. Last webinar, about a month ago, I looked at demographics for various countries around the world. And there were about 170, 180 countries. Well, some of the graphics I want to show you today get very crowded, very complicated when you have that many objects to try to display. So I thought it was more useful in terms of trying to demonstrate the capabilities of these procedures to cut the data set size down again. So what I did is I went out to the internet and found information about the 50 states that comprise the United States. Collected information on a state-by-state basis about things like the percent of people that completed college, income, non-English speakers, median age, that sort of thing. In fact, we're going to be looking at a total of 13 variables today. 13 variables that characterize each of the states. We're going to be looking at the education of the population. That's going to be the percent completing college. the per capita income, the percent of people living in urban areas, the population density, the percent of people in a particular state that don't speak English, the median age, the unemployment rate, the percent of the population that are female, the crime rate, the percent of the GDP that comes from manufacturing. We'll be looking at infant mortality and poverty rate. Actually, those 12 variables are the variables that will characterize each of the states, each of the observations. There is a 13th variable that we'll be looking at when we get to the classification problems, and that is the results of the presidential election we had about a year ago, the election of 2012, where Barack Obama was running against Mitt Romney. And one thing we'll be interested in knowing is whether we can use these 12 characteristics of the states to predict who a particular state might vote for. Okay. I hope you find this interesting. Now, when you look at the United States, there's actually quite a bit of variation amongst the states. What I'm showing you here is actually a graph of the percent of the population in the various states that live in urban areas. That percentage ranges from about 35% up in Maine to about 95% in states like New Jersey, California, Nevada, and so forth. What I've done here is actually color-coded the states from blue to red according to the urban percentage. That's one of the 12 dimensions that we'll be working with in terms of actually characterizing these states. Another interesting dimension is the percent of the population that are female. I was a little surprised when I first saw this graph, but there's actually quite a bit of variation amongst the 50 states in the United States in terms of how many people, or what percent of the population are women versus what percent are men. It ranges actually from about 48% female up in Alaska, and there's Alaska down here, to nearly 52% in most of the northeastern states and also states like Alabama and Mississippi. A third interesting statistic that I thought I'd show you is the poverty rate. There's quite a bit of variation also in the percent of the population that are below what the government defines as the poverty level. That ranges from a low of about 8% in states like New Hampshire, New Jersey, Maryland, and so forth, up to over 20% in states like Mississippi, New Mexico, Louisiana, and so forth. So the 12 different characteristics that I've selected do vary quite a bit amongst the 50 states in the United States. Now, as always, before I look at any statistical methods, I want to create some graphs. The graphs I just showed you looked at the variables one at a time. What I'd like to do now, though, is show you a graph where we can look at all 12 variables at a time. The procedure in Statgraphics that's quite useful for doing that is the procedure called the star glyph. What the star glyphs is a graphical representation of multivariate data on a case-by-case basis. So in a moment I'm going to go to Statgraphics and I'm going to generate a star glyph for each of the 50 states to demonstrate the value of those 12 variables. Now, the key to this is I'm going to draw a glyph, an image like you see on the screen here. And it's going to show the values, the numeric value, on a state-by-state basis for everything from education through income per capita through poverty rate and so forth. Now, what you're seeing is what the glyph would look like for a state that had a maximum value on all 12 characteristics. When we actually plot this glyph for a particular state, the size of the glyph along any particular axis will be proportional to its relative value on that particular variable. So if you look, for example, at the 12 o'clock position here, where you see education, a state that was at the median value for education would be only come out to about here. If education was quite small, it wouldn't come out very far at all. It's a very nice procedure for being able to demonstrate on a case-by-case basis, as I said, the value of multiple variables. Okay, now at this point I'm going to actually switch over to Statgraphics, Centurion, and you see that I've loaded up a file called US_state_data. This data file, by the way, is currently on our website on the webinars page, together with the slides that I'm going to be showing you off and on from my PowerPoint presentation. In order to create the glyphs, I'm going to go to the Plot menu, to the section on Multivariate Visualization. You'll see there's a selection for star glyphs and sunray plots. The data input dialog box, if you go there, is going to ask me first off, what columns do you want to use to create the glyphs? And I'm going to choose the 12 columns ranging from education to poverty rate and use those to create the stars. I'm also going to take the states and use the names of the states to label each of the glyphs. If I now press OK, OK again, it's created the star glyphs for me. Now, before I do anything else, I'm going to make this plot a little bit larger so it's easier for you to see. I'm also going to push graphics option, the right mouse button, go to graphics options, change the font size to 7, make it a little bit more readable. Now, what you're looking at is the 12 variables, and everything from education through the poverty rate, on a state-by-state basis. Now, the interesting thing of this sort of plot is you can look at it and begin to identify states that are similar to each other. For example, if you look at the star glyph for New Jersey, where I used to live, you'll see that that glyph is very similar in shape to the glyph for New York. Fairly similar to that for Connecticut and several of the other states. If you see a very similar shape, it means, at least with respect to those 12 characteristics, those states are similar. On the other hand, if I look at the glyph for Virginia, where I live now, it's got a considerably different shape. And one question I asked myself when I first created this plot was, what state is most similar to Virginia? And if you look around through the 50 states, you will find out that, at least it's my judgment, that Minnesota seems to be most similar to Virginia. Now, I must tell you that surprised me. I know Minnesota and Virginia aren't very similar with respect to weather. It gets a lot colder up in Minnesota than it does in Virginia. But at least with respect to the 12 demographic variables that I'm looking at, Virginia and Minnesota are actually quite similar. So it's an interesting plot, an interesting way of looking at multi-dimensional data when you don't have too many observations. You can imagine this can get crowded if you have an awful lot of observations. But for something like the 50 states, it's really a perfect way, I think, of looking at multivariate data. Okay. As I said, I always think it's important to begin by looking at our data before we start doing any real statistical methods. Now, though, I'd like to go back and talk about the first major procedure that I'm going to cover in this particular webinar. The first major procedure I'm going to cover is called cluster analysis. Cluster analysis is a method for assigning objects to groups. Basically, what I'm going to do is I'm going to take my 50 states and put them in groups. And I'll try to put them in groups in such a way that the objects in the same group are more similar to each other than they are to objects in other groups. So I'm going to take my 50 states and try to group them into groups of similar objects. Now, some of the natural questions that one would like to ask, or answer actually, with a cluster analysis is, first off, how many natural groups are there? At least with respect to these 12 variables, how many natural groups do there appear to be that I could put these 50 states into? And then secondly, of course, which objects belong to which groups is also quite an important question. Okay. Now, we're going to do this, again, by going back to Statgraphics. So let me go back to Statgraphics. Let's minimize that, the star glyphs for a moment. The place where you find the cluster analysis procedures is under Describe on the main menu. It's under Describe, Multivariate Methods, Cluster Analysis. Now, the first dialog box that comes up is going to be the data input dialog box. It's going to ask me which variables I want to use to cluster the states. And I've decided to tell it to take everything from education down to poverty rate, the same 12 variables I just plotted the glyphs with, and use those to divide the data up into groups. At the same time, I'm going to take the column called state and put that in as the point labels. Okay. Now, the second dialog box I'll see is the analysis options dialog box. And here I need to tell it what method I want to use to put those states into groups. There are a total of 7 different methods that Statgraphics offers. Everything from the nearest neighbor down to the method of k-means. The first 6, all the methods except for the k-means, are what are called hierarchical clustering methods. They'll start with every object, every state in a separate group. So they'll start with 50 groups. It'll then take the 2 groups which are most similar and put those 2 states into a single group. So after the first step of the algorithm, we'll reduce the number of groups from 50 down to 49. It'll then take those 49 groups and ask, okay, which 2 groups are most similar, and it will put those together. And eventually it will go down to whatever number of clusters you ask it to do. And if you ask it to put everything into a single cluster, it'll eventually put all 50 states into one cluster. It also asks me, how do I want to measure the distance between objects? The traditional way to do that is to use what's called the squared Euclidean method, which is, the a squared plus b squared equals c squared type approach. The normal way we would measure distance in a multidimensional space. I can cluster observations or variables, meaning I can either cluster states, put the states into groups, or I could put the 12 variables into groups. In this case, I'll be clustering the observations. And finally, it wants to know whether I want to standardize the variables first before I measure the distance between them. And since everything is measured in different units, I definitely want to do that. Standardize means you take a variable, subtract its mean, divide by its standard deviation. which basically it gets everything dimensionless on the same scale. Now, as far as the methods that I want to use, nearest neighbor, furthest neighbor, or whatever, it's usually a good idea to try several. Where they differ, incidentally, is how they measure the distance between clusters, between groups. The nearest neighbor method will take two groups of states and define the distance between them as the distance between the nearest points in each of the two groups. Furthest neighbor, on the other hand, would define the distance between the groups as the furthest distance between one point in one group and one point in another group. And they can give you dramatically different results, as you'll see. So let's just take all the defaults to start with, the nearest neighbor, and press OK. And when it offers us the tables and graphs, we're also going to press OK. Now, the most interesting thing you're going to get out of the cluster analysis typically is something called a dendrogram. A dendrogram will show the distance between points when they are placed in the same group. Now, the way you read this is look over here on the left. The first two states that are shown on the left are Alabama and Arkansas. Those two were grouped together at a distance of a little over 1, meaning those two states were put together very early. I think that was probably the first combination. Alabama and Arkansas were combined into a single group. At about the same time, South Carolina and Tennessee were combined into a single group. A little bit later, those 4 states were all combined into a single group. Then later on, they were combined with Kentucky and so forth. Now, unfortunately, this nearest neighbor method didn't do exactly what I wanted it to do, which was hopefully get a good grouping of the states. Because if you look way on the right, you'll see that the last combination of groups had Utah being combined with all the other states. That was actually the last step. The second to last step was to combine Alaska with the other steps. Now what that means is that if I press the right mouse button and go to Analysis Options and tell it to stop after 3 clusters, I'll just change that to 3, Utah would end up in its own cluster, Alaska in its own cluster, and all the 48 other states would be in their own cluster. Now that's not really what I wanted to achieve. I really wanted to separate these states into major groups. Unfortunately, the nearest neighbor method really didn't do it for me. On the other hand, if I push the right mouse button, go back to Analysis Options, tell it I want to use the furthest neighbor method, and let's reset the number of clusters to 1. The furthest neighbor method actually does more what I wanted to do. Okay? The last step in the furthest neighbor method was actually to take this group of states here, combine it with this group, all the rest of the states. You can see, though, if you look at this particular plot, that it appears that there are pretty much 4 natural groupings of states. There's a group of states here, there's a group of states here, there's a group of states here, and there's a group of states here. 4 approximately equal sized groups, which is really what I was hoping to achieve. Now, if you're not sure how many groups, natural groupings there are, if you push the Tables and Graphs button, you can ask for something called the agglomeration distance plot. This plot will show you at each step of the algorithm when groups are formed what the distance was between the groups. And you can see early on when states were combined, the distance was actually quite small. But once it reached the last few stages, the distance between the groups was actually quite large. Now, what you're looking for in these sorts of plots is a real knee. And you can almost see a real sharp change in the slope right about here. This would have been the distance when there were 2 groups being combined, when there were 3 groups, when there were 4 groups. So it also suggested a natural grouping of my states would be into 4 groups. Well, let's go back to the dendrogram for a moment. Let's press the right mouse button, go to Analysis Options, and ask it to group the states into 4 clusters. That basically says stop the algorithm after you've divided the states into 4 groups. And as I said before, you can now see basically natural groups. Now, I'd like to show you, of course, what these groups look like on my maps. So I'm going to go up to the Analysis toolbar, push the button that says Save Results, and ask it to save the cluster numbers. What I just asked it to do was to save the cluster numbers back in the data book. I can now go to the Describe, Categorical Data, Map by State, which is one of the procedures we have in Statgraphics, and ask it to map the cluster numbers by state. Okay. Push OK a couple times, and you'll actually see now a map of how the states were allocated to the 4 different groups. Now, they were allocated based upon demographic variables, but you can see that the groups also correspond to different areas of the country. The red group you can see is pretty much all the western states and the southwestern states, together with Missouri, but not including Oregon, which is sort of interesting. The second group, well, there's another group of states which is primarily the southeast, except for Florida. There's a green group which is the north central states, together with my state of Virginia and a few of the New England states. And then finally group 3, which is mostly the northeast, plus Ohio, Illinois, and Florida. Incidentally, I was real curious about Oregon, why it didn't appear to be similar to the rest of the western states. Turns out that Oregon actually has a lot of manufacturing. If you look at the percent of the GDP in Oregon that has to do with manufacturing, it's really quite high. Actually, at least in the data I was looking at, Oregon and Indiana, this state right here, had the highest percent manufacturing. So the cluster analysis, when it did the grouping based upon my 12 demographics, actually assigned Oregon to the group that contains mostly the manufacturing states in the Midwest and also down there, the southeastern states. Okay. All right. That was a hierarchical cluster, and it appeared that there did, at least using the methods I used, that there were about 4 natural groupings of the states. Okay. Now, there is one other way to do clustering, and that is to use the method of what's called k-means. Rather than starting with every object in a different group, if you use the method of k-means, what you do is you start with a set of typical objects. You decide, for example, okay, I want to group things into 4 groups, let's say. You start by picking 4 objects, 4 different states, to seed the groups. You then assign each of the other objects to whatever group has the nearest seed. Okay, so you take all the other states and assign them to the most similar cluster, the most similar seed. You then compute the centroids of the groups. That's the location of the means on each of the 12 variables. And if any objects are closer to the centroid of a different group than they are to their own group, you move them to the other group. And actually, it's an iterative procedure. You keep going on steps 3 and 4 until there's no change. Now, if you do it this way in Statgraphics, the first thing you need to do is tell it, of course, you want to use the method of k-means. The second thing you need to do is you need to press the seeds button. The seeds button is the button where you tell it what states you want to use to form the initial groups. And I decided when I did it, and as you'll see in the notes, to use California, New York, North Dakota, and Texas. They are geographically about as far apart as you can get, and in other ways they're quite different states as well. So that's row 5, row 32, row 34, and row 43. Now, to show you how to do it, let me go back to Statgraphics. Let me go back to my cluster analysis. I'm going to press the right mouse button, go to Analysis Options. I'm going to select this time k-means, leaving the number of clusters at 4. Okay. I'm going to press the Seeds button, and it's now going to be asking me for 4 numbers. What row numbers do I want to use as seeds? Well, I want to use row 5, row 32, row 34, and row 43. Okay. I'll then press OK and OK. And it's now done the assignment. Now, you won't be able to see a dendrogram. Dendrogram doesn't apply. But you will be able to see that it has assigned 11 members to the first cluster, 9 to the second cluster, 13 to the third cluster, 17 to the fourth cluster. And if you'd like to see what it did, I should go push the Save Results button again. And this time I'm going to save the cluster numbers in a column I'll call Clus Numbers K. How about? Now let's go back to the map of the states, go to the Data Input dialog box, put in Clus Numbers K instead of Clus Numbers, and you'll see what the method of k-means has done. It's a little bit different. You'll see that Oregon is still in the cluster with the southeastern states, but Idaho has actually joined that cluster. There's also a couple switches here in the Midwest. Basically, it's the same clustering of the states. Only a couple states have changed. Incidentally, it was sort of interesting. I had started with New York, California, North Dakota, and Texas as my seeds. You notice that Texas actually moved out of the green group, which was its initial group, into the same group as California in that iterative part of the assignment. So the initial states don't necessarily stay in different groups. Okay. Well, that's what I wanted to say about a cluster analysis. Let me minimize those windows for a moment and go back to my PowerPoint presentation and move to the second major topic of this webinar, which is classification. The classification problem deals with the assignment of objects to known groups. And here's where I'm going to pull in actually my election data. I know that certain states voted for Barack Obama in the last election. Other states voted for Mitt Romney. What I'd like to do now is come up with a method based upon the 12 variables that I've been looking at of determining what states are likely to be Obama states, what states are likely to be Romney states. Now, the goal of this typically includes understanding what differentiates the groups. How are Obama states different from Romney states? And in many cases, trying to predict group membership for unclassified objects. Now, one of the common sort of classic applications of classification is when a credit card company looks at its customers and tries to mathematically determine what characterizes a client that pays their bills on time versus a client that doesn't pay their bills on time, with the goal of using whatever methods they come up with to determine for new customers, for potential customers, whether they're likely to be a good credit risk or not. Very important applications of the methods we're going to be looking at. Okay? Now, the methods we will be looking at will be three. First off, I'm going to look at something called a discriminant analysis. That's found on the Statgraphics Centurion menu under Relate. It's based upon Fisher's linear discriminant functions. Okay, and as we'll see, it tries to take the variables that characterize the objects and build linear combinations of those variables that best differentiate between the groups. Secondly, I'm going to look at a neural network classifier, which is also on the Relate menu in Centurion. It uses something called a Bayesian classifier. The Bayesian classifier takes the information from the data, combines it with a prior probability. Your prior assessment of the likelihood that an individual, for example, will be creditworthy versus not creditworthy, and also with the costs of incorrectly classifying observations. As you can imagine, the cost of deciding that someone is creditworthy when they're not is likely to be different than deciding they're not creditworthy when they really are. Okay, so one nice thing that the neural network classifier introduces into the problem is costs. I'm also going to give you a brief look at a companion program to Statgraphics called Uniwin. One thing that Uniwin includes is methods for dealing with qualitative factors in addition to quantitative factors. As you'll see, as in the Centurion procedures, it's assumed that all of the factors are quantitative. Things like, population density, income, and so forth, the things that we've been looking at. Uniwin allows you also, though, to use some qualitative factors. Okay. Now, the first procedure we're going to look at is going to be a linear discriminant analysis. What a discriminant analysis does is it constructs linear functions of the variables that characterize the objects that you want to classify. Actually, linear combinations of the standardized variables, which means you start not with the raw x's but with the z's, where the z's are basically each of the factors, each of the variables, minus their means divided by their standard deviations. The nice property of the standardized classification variables is then you can look at the coefficients in the discriminant function and determine just how important a particular variable is with respect to that discriminant function. The functions are derived mathematically so as to maximize the separation of the groups. We try to come up with linear functions, linear discriminant functions, that separate the different groups as well as possible. And I've also made a note here that if there are G groups, there are G-1 discriminant functions. Now, if I try to take my election data where I had some states that go for Romney and some that went for Obama, there'll be only two groups, so there'll be only one discriminant function. But I think you'll find that it's actually quite interesting. Now, before I do that, though, I want to show you one more graph, and that is the results of the election. This graph shows what happened in the 2012 election, which states voted for Obama, those are the blue states, and which states voted for Romney, those are the red states. And you can see that, again, geographically, there was some clustering of the states. All the states in the Northeast typically went for Obama. On the West Coast, they went for Obama. In the Midwest, except for Indiana, they also went for Obama. However, if you look down in the South, in the Plain states, up here in Montana, Idaho, Wyoming, and so forth, that was where they were strong for Romney. The goal, though, is going to be now to take the 12 variables I've been looking at, the 12 demographic variables, and come up with a mathematical equation that I could use to predict whether a state would be an Obama state or a Romney state. Okay, now let's go back to Statgraphics, and I'll show you how we do this. The first thing we do is we have to find the discriminant functions. Well, the discriminant analysis is under Relate, Classification Methods, Discriminant Analysis. Now, the data that I'm going to use, first thing it's asking me for is a classification factor. And that's going to be election 2012. That's either Romney or Obama for each of the 50 states. The data that I'm going to use are education down through poverty rate, the same 12 variables that I looked at when I did the clustering. I'm also going to put where it says point labels state. Let's press OK. Now, the second dialog box I'll see is the analysis options dialog box. And it's asking me, do I want to use all of the variables, or do I want to use some sort of variable selection procedure? Now, the variable selection procedure is very much like what we have in multiple regression. It's a stepwise selection if I want to use it. And there are two stepwise selection procedures. There's a forward selection, where basically I bring variables in one at a time until bringing in any other variables isn't helpful anymore. And there's also backward selection, where I start with all my variables and I throw them out one at a time if they're not statistically significant, till I get down to a group of variables that are statistically significant. Very similar to the stepwise regression that we have in the multiple regression procedure. Okay, let's start, though, by doing all the variables. And when it asks what tables and graphs I want, I'm going to ask for the analysis summary plus the discriminant functions. Okay. Now, you will see down in the bottom left the coefficients of the discriminant function. You'll see actually what it calls the standardized coefficients up here and the unstandardized coefficients down below. If I scroll down to the Stat Advisor, I can also see in the Stat Advisor it's actually written out the equation of that discriminant function. Now, what's interesting here, I think, is to look at the coefficients of the discriminant function. The magnitude of the coefficient basically is related to how important that coefficient is in the discriminant function. The coefficient, largest coefficient, actually corresponds to poverty rate. Poverty rate enters with about a minus 1.24 into the discriminant function. Now, as you'll see in just a moment, the discriminant function goes from negative values to positive values. Negative values end up being favorable to Romney, positive values for Obama, and that's completely arbitrary. What this says, though, if I look at that negative coefficient, is as the poverty rate goes up, the discriminant function goes down, meaning that if the state had a high poverty rate, it would be more likely to vote for Romney than it would for Obama. Okay? On the other hand, if you look at some of the other large coefficients, here you see percent female. Percent female is positive, meaning the higher the percentage of females in the state, the more likely that state was to vote for Obama. Now, I'm not implying a causal relationship. There might be, there might not be. As in every other mathematical statistical model, there could be other factors at play, third factors driving both variables. But it does turn out that the states with the highest percent female ratios typically went for Obama. Now, you have other problems here. You have the same problems, incidentally, of multicollinearity here that you would have if you fit a multiple regression. Take a look, for example, on the coefficients on urban percentage and population density. The urban percentage coefficient is positive, implying that the more urban areas there is in the state, the more likely it is to go for Obama. On the other hand, population density is negative, implying that the higher the population density, the more likely it is to go for Romney. Now, I was curious about that, and I actually looked at those variables. Those variables are positively correlated, okay, and fairly strongly correlated, which means that, truthfully, the same way it would be dangerous to interpret the coefficients in a multiple regression when you had variables that were highly correlated, we're going to have the same problems here in terms of trying to interpret the individual coefficients. Now, it doesn't mean it's not going to do a good job discriminating the groups. It just means that we have to be somewhat careful on the interpretation of the coefficients. Okay, now, I'd also like to go over here and show you the discriminant function plot. Well, by default, it's sort of assumed that I have at least two discriminant functions. I'm going to have to push the right mouse button, go to Pane Options, and tell it actually to put discriminant function 1 on both the x and the y-axis. If you do that, you actually get a fairly useful plot. Okay? This is a plot actually of the 50 states and the value of that discriminant function. The discriminant function goes from a low of about minus 3.7 to a high of about 3. It's color-coded, blue for the states that went for Obama, red for the states that went for Romney. And you can see there is a line around 0 which does a pretty good job of dividing the blue states from the red states. Now, there's a little bit of overlap, meaning there would be a little bit of misclassification based upon this single discriminant function. There's a little bit of overlap of the reds with the blues. But by and large, the discriminant function separates the Obama states from the Romney states. Okay. Now, the next thing I decided to do, because this was fairly complicated, was to reduce the number of variables. I started with 12 variables. I'm not sure that 12 are really necessary. So the next thing I did is I pushed the right mouse button, went to Analysis Options, and asked it to do a backward selection. A backward selection will start with all the groups, all the variables throw the variables out one at a time, starting with the least significant variable, then the next significant variable, and so forth, till it gets down to a subset of the variables, all of which are statistically significant. Well, if I run the backward selection, you'll find that it actually reduces the model from 12 variables down to 6. It actually threw out 5 variables to get a simpler mathematical model. A simpler mathematical model that it turns out does almost as well as the mathematical model involving all 12 variables. Okay. Now, there's a little bit more that I need to tell you about this. I need to talk a little bit more about classification. So let's go back to PowerPoint for a moment. And I'll go down through what I just did until I get to the slide that talks about classification functions. I can take the discriminant functions, the mathematical discriminant functions that I've derived, and do a little mathematics, and come up instead with what are called classification functions. Classification functions allow me to score each object, in this case each state, for either Obama or Romney. I can take a linear combination, and in this case it's a linear combination of the original variables, not the standardized ones. It doesn't matter. I could have done it that way, but it's on the original variables. Okay? And if I take a particular state, put in its characteristics, I can come up, for example, with the state of Virginia, get a score for Obama and a different score using a different classification function for Romney. Okay? Now, this is useful for classifying the objects. And in fact, objects will be assigned to whatever group gives the largest value of C sub j times a prior probability, where prior is the prior probability that it belongs to group J. Now, in the case of Romney and Obama, I'm going to use a non-informative prior. I'm going to assume there's a 50% chance that a state goes for Romney and a 50% chance that it goes for Obama. You can imagine, though, if you're using this to score creditworthiness of individuals, that there may be different probabilities that a randomly selected individual would be creditworthy versus not creditworthy. And you might like to take those prior probabilities into account. Okay. Now, let's go back to Statgraphics. I'll show you where we go to find that. What we do is we go to the Tables and Graphs button, and I'm going to ask for two things. I'm going to ask for a classification functions, and I'm going to ask for a classification tables. The classification functions show you those coefficients in the equation we were just looking at. The coefficients for the Obama classification function and for the Romney classification function. Okay? Well, those are in unstandardized units, so the coefficients themselves aren't that useful. What is useful is to look down here now at the classification table. The classification table will show you each of the states, the scores for Romney and Obama, and will assign each particular state to whatever candidate had the highest score. So, for example, look at this row down here. This is Alabama. Okay? Alabama voted for Romney. That's how it actually turned out in the election. It had a score of 9,063.2 for Romney, 9,058.1 for Obama. Since it had a higher score for Romney, it was assigned to Romney. And you also get a posterior probability here. Mathematically, we determined that the probability that Alabama would vote for Romney was well over 99%. That state was not in play during the election. It's a solid Republican state and definitely went for Romney. The table up the top actually summarizes how well we did. It says that we classified correctly 94% of the states. In fact, 26 states voted for Obama. Of those, our discriminant function would have classified 25 properly. But one of the states that went for Romney, we would have actually have assigned to Obama. Of the 24 states that actually voted for Romney, 22 would have been assigned mathematically to Romney. 2 we would have missed. If you're curious about the states, incidentally, that we missed Missouri. They voted for Romney. We would have assigned Missouri to Obama. Nebraska, they voted for Romney. We would have assigned them to Obama. And New Mexico. New Mexico was assigned to Romney. They voted for Obama. So we missed 3 out of the 50 states. Okay. Now, I should point out that this 94% here is sort of may overstate how good the discriminant function would be if we tried to predict additional observations. Now, of course, there are no additional states to try to predict. But if you were doing creditworthiness and so forth, there might be in other individuals that you want to predict. Because my 50 states have been used to actually fit the discriminant function, I'm likely to classify a higher percentage of those correctly than if I took some random new observations. Well, one thing you can do to test how good it is in predicting new observations is to take out some of the objects. For example, take the last 10 states and don't use them to fit the model. Fit the model using only 40 of the states. The 40 states would then be called the training set. They're used to train the discriminant function, if you like. And see how good that discriminant function would be in predicting the states that you didn't use. Now, I can do that pretty quickly in Statgraphics. I can go, for example, back to the data book and perhaps go over to the column where I had Romney versus Obama. There it is. And I decided arbitrarily to delete the entries for the last 10 states. Now, it would have been better to maybe have taken 10 random states rather than the last 10, but I wanted to do this quickly. If I now click back to the discriminant analysis, you'll see from the classification table that it's now classified only 40 states, 22 of which voted for Obama, 18 for Romney. And it didn't do quite as well. It did about 87.5%. On the other hand, if I go down to the bottom of the table, you'll see the 10 states that were not used. You can see no entry here for actual. The 10 states that were not used to fit the discriminant function. And yet I still have the information on the X variable, so I can still make a prediction. So I can still predict South Dakota going for Romney, Tennessee going for Romney, and so forth. And incidentally, of those 10 states, 8 are correct, 2 are wrong. So in the validation data set, okay, we have basically 80% success. Unfortunately, less than we would have guessed from the training set, and that's always the way it's likely to be. Okay. Well, that is the linear discriminant analysis in Statgraphics. Okay. I want to show you a second procedure for doing classification, the neural network procedure. And to do that, let me close off everything I've done so far. I need to open up another clean version of that data now that I erased things. All right, now I've got another clean version. The second classification procedure I want to talk about is the neural network classifier. The neural network classifier implements a non-parametric method for classifying objects. Rather than coming up with linear combinations of the variables, it uses a non-parametric algorithm. And it bases its classification on three quantities: the estimated density function in the neighborhood of the object, the prior probabilities of belonging to each group, and the cost of misclassifying cases. Now, what's particularly new about the neural network classifier, new and different compared to the linear discriminant analysis, is number one here, estimating the density function in the neighborhood of the object. Now, what we mean by that is the following. If I was to take my 50 states and plot them in the space of my 12 variables, my 12 predictor variables, I'd have 50 points in a 12-dimensional space. Based upon those 50 points, I could estimate in that 12-dimensional space, at any point in that 12-dimensional space, how likely it is that I'd see a Romney state at that point versus how likely it is that I'd see an Obama point. And what you do when you estimate the density function is you basically pick a point in 12 dimensions, and you look all around that point at its nearest neighbors, at the other points that are nearest to the one that you're trying to predict. If you see a lot of Romney points in the vicinity of what you're trying to predict, you say, well, okay, if I'm here, I'm likely to vote for Romney. On the other hand, if you see a lot of Obama points in that neighborhood, you say, well, I'm likely then to vote for Romney. Okay? And what it does is it takes each one of the states, okay, finds where it's located, looks in the neighborhood of that state to try to figure out whether it's close to Obama states or Romney states. Now, there is one tunable parameter when you do that. It's a parameter called sigma. Sigma basically is the width of the weighting function it's going to use when it looks for nearest neighbors. If sigma is large, it's going to look far away from a point for neighbors. If sigma is small, it's going to look only relatively close to that point. And you can play around with sigma, make it smaller or larger until you see the best results with respect to the data that you're trying to classify. Okay. Now, I actually made a picture of a couple bivariate densities for you. I didn't do it in 12 dimensions. I only did it in 2 dimensions. Okay? Hang on for a second. I'm getting a message that I may not be sharing my screen anymore. That there's polling open so that you might not be seeing my screen. Craig, would you let me know, please, if there's a problem with respect to everybody seeing my screen?
You can go ahead. You can go ahead. The poll is over.
Oh, okay. Yeah, I guess if you start a poll during the webinar, you can't see my screen. Okay, good. I want to make sure that you can see what I'm doing. Okay. Anyway, I was trying to explain what a bivariate density is. And as I said, I can't plot the bivariate density for all 12 predictors simultaneously. What I did is I just picked two to illustrate for you what I mean by a density function. I picked urban percentage and poverty rate. This axis here is urban percentage. This is poverty rate. What you see here is a bivariate density function for Obama, and over here a bivariate density function for Romney. In the case of Obama, what it's done is it's basically taken all the states, all 50 states, and looked at where they are located with respect to urban percentage and poverty rate. Okay, and evaluated at every point over the grid how many Obama states there were in a particular region and how many Romney states there were. Okay, the height of the surface is proportional to the probability of seeing an Obama state at a particular point or the probability of seeing a Romney state at a particular point. You can see actually that the probability of seeing Romney points is higher where the urban percentage is low than is the probability of seeing an Obama state, it being an Obama state. Okay. On the other hand, with respect to the poverty rate, you can see some differences here too, but the dramatic difference is really urban percentage. For the states with a very low urban percentage, they turned out to be mostly Romney states, and the higher urban percentages were mostly Obama states. This happens to be for one particular value, sigma, just arbitrarily I picked 0.5. Anyway, that's what the bivariate density looks like. Now, I should also make a point about why this is called a neural network. It's called a neural network because, at least in some sense, the way it's going to process data is similar to the way your brain is going to process data. There is an input layer, a pattern layer, a summation layer, and an output layer. The 12 variables, the 12 demographic variables that I'm going to use as input to the algorithm are going to help me, well, are the information that I'm going to need to process in order to classify states as being Romney states or Obama states. The pattern layer are the 50 cases that I have to tune my algorithm. The summation layer is where I take all of those variables, analyze the patterns, and determine a score for Obama versus Romney. And then eventually, depending upon the scores, I'll come up with some output. I'll determine which are likely to be Romney states and which are likely to be Obama states. So in a very real sense, it's like what your brain would do. It would bring in information, it would look at the patterns, it would summarize the information, and then make a decision about what states are likely to be Romney states and what states Obama states. Okay, now let me show you how that works in Statgraphics. It's actually quite similar to the discriminant function. In fact, it's located in the same place. I'm going to go to Relate, Classification Methods, Neural Networks. Now, I'm going to take those same 12 variables, education through poverty rate, and tell it that that's the input layer. I'm going to take election 2012 and tell it that's the output classification. Okay. The next dialog box I'll see will be the analysis options dialog box. Here I can specify the prior probabilities. Well, I'm going to say they're equal for all the groups, but you could put in something else. You can specify error costs. Again, I'm going to say the cost of misclassifying is going to be equal for every group, but it could be different. And finally, down here, this is the most interesting section. I can either tell it what sigma to use by putting in 0.5 or something like that, or tell it to train using jackknifing. Now, if it trains using jackknifing, what it will do, it'll start with a particular value of sigma. It will, one at a time, remove each of the 50 states, run the procedure, and try to classify the state it removed. So it'll run the procedure 50 times at a particular sigma, removing one state during each run, and then determine how many of those states that have been removed would have been classified properly based on the other 49 states. It'll try that with a particular value of sigma, maybe 1, then it'll try sigma 0.9, then it'll try 0.8, then 0.7, and so forth, until it finds the value of sigma that gives the highest percentage of correct classifications. That procedure is called jackknifing. All right, well, we'll let the program do the work. Again, I'm going to take all the defaults. And of particular interest is going to be the classification table. It will tell me basically how well it did in terms of classifying these particular observations. Well, unfortunately, I'm not all that impressed by what it did. It got only 78% of the states correct. It actually missed 11 of the 50 states. In fact, 8 states that voted for Obama, it assigned to Romney. 3 states that voted for Romney, it assigned to Obama. Not nearly as good as the discriminant function procedure. Now, why is that? Now, I thought about that for quite a while. Why would this neural network procedure not be up to snuff compared to the linear discriminant function? And I realized that basically what it has done, it has taken each of those 12 variables and weighted them equally. Basically, it's looked for nearest neighbors in a 12-dimensional space. Well, we saw in the discriminant function, you may remember when we did the backward selection, that 5 of those variables weren't statistically significant. And therefore, I wondered what would happen if I took out those 5 variables. Well, let's go back to the input dialog box, and let's take out, I happen to know what 5 variables were not significant. I'm going to remove those 5 variables and leave it just with the same 7 variables that I got when I did a backward selection in the linear discriminant analysis. Now if I press OK, you'll see that it actually does much better. It now gets 86% of the states right, rather than, what was it, 78%. It still missed 7, but that's much better performance than on all 12 variables. Which leads me to believe that I better put in a stepwise selection procedure into this neural network. I mean, you can do it by hand right now, but it would be nice if it would automatically remove variables and see if it could do better. Okay, and it definitely did appear to do better. Now, there's also, though, one really nice plot in the neural network procedure, which you might like to see. If I push the Tables and Graphs button, it's called the classification plot. What the classification plot does is show you where it figures you'll find Obama states and where it figures you'll find Romney states. Now, what it's doing is it's actually plotting the regions where it would decide it was Obama versus Romney with respect to two variables, in this case, urban percentage and population density, with all the other variables held constant at their mean values. So except for urban percentage and population density, everybody is held at its mean. But now it's showing you what the trade-off is between Obama and Romney. And wherever it's blue, if a state had that combination of urban percentage and population density, we would assign it to Obama. And if it had something in the red zone, that would be Romney. Now, it's interesting. The division is actually fairly linear here. It doesn't have to be. We're doing a non-parametric density estimator. But actually, with respect to urban percentage, you can see it's going to classify observations, if they're in the blue region here, as being Obama, and if they're in the red region here, Romney, and a fairly linear boundary between them. If I push the right mouse, go to pane options, try a couple others, though, it's a little less linear. Let me try median age and employment rate instead. Okay, switching variables, you can see now that the boundary between where it would predict Obama and where it would predict Romney is nonlinear. And in fact, in some cases, it'll be even stranger than this. It's possible that there'd be a blue area down here, a red area in the middle, and another blue area at the top. If I got that, I think it probably wasn't doing a very good job. This is a pretty good-looking classification plot that really does seem to divide the Romney states from the Obama states. Anyway, you've got two methods in Statgraphics Centurion for doing classification. You have the linear discriminant functions. You have the neural network functions. Now, there's one other classification procedure I wanted to talk about, and that's the one that's contained in Uniwin Plus. Uniwin Plus is a companion program to Statgraphics in the sense that the data input is typically Statgraphics data files. It's a software package written by a long-term colleague of mine, Christian Charles, who's located at a company called Sigma Plus in France. He is the local representative in France for Statgraphics, has been for a long time. Has also put together a very nice program called Uniwin Plus to do some multivariate procedures that Statgraphics does not do. In fact, I believe that may have been his motivation for doing it. He wanted to do certain analyses that were not currently in Statgraphics. One of the procedures that's quite helpful in Uniwin Plus right now is the ability to handle qualitative variables. As you've seen so far, everything I've been dealing with respect to cluster analysis, classification, and so forth have been quantitative. However, there are times when things are not naturally quantitative, they're qualitative. And as an example of that, I went out to the internet and went to one of the government agricultural sites and looked at what the major farm products were in each of my 50 states. Okay, and I picked 5 products: cattle, corn, dairy products, greenhouse plants, and poultry. And I classified each state as being primarily a cattle state, or a corn state, or a dairy state, or a greenhouse plant state, or a poultry state. And here you see a picture, actually, of the most important farm product of those 5 in the particular states. Now, there were certain products like rice, which I think was very important in Louisiana, and tobacco in North Carolina. But if it was just isolated like that, I left it out and classified those states as being one of the 5, depending upon what the next most important product was. Okay. If you want to introduce farm product into the cluster analysis or the classification procedure, you're going to have to use Uniwin Plus because it's capable of handling qualitative variables where the Statgraphics procedures, at least currently, are not able to handle that. Okay, now, what I did, therefore, is I created a new file. I created a file called US Data for Uniwin. You may notice on this slide also that it's an SF6 file. The current version of Uniwin requires you to save your Statgraphics file in an SF6 format, which you can do very easily while you save the data file from within Statgraphics. You just tell it the file type you want is SF6. That was the major file type we used in version 15. Christian does tell me that in the next version of Uniwin, it'll read the SGD files that version 16 creates. But it's not hard to create an SF6 file right from within Statgraphics. The second thing I needed to do, though, is I needed to code everything as integers. So what I did is I started by looking at the election of 2012. I changed the word Obama to a 1, Romney to a 2. I introduced a brand new column, major farm product, where I put a 1 if it was a cattle state, a 2 if it was a corn state, and so forth. A number between 1 and 5, depending upon what its major farm product was. For the other variables, for urban percentage, population density, median age, and so forth, to make them qualitative, I changed them from numeric values into quartiles. Now, what do I mean? What I mean is I took a particular column like urban percentage, and if the numeric value for a particular state was between the minimum and the lower quartile, that's the 25th percentile, I gave it a 1. If the state was between the 25th percentile and the 50th percentile, I assigned it a 2. If it was between the 50th and the 75th percentile, I assigned it a 3. If it was between the 75th and the maximum, I assigned it a 4. So approximately a quarter of the states got a 1, a quarter got a 2, a quarter got a 3, a quarter got a 4, and I did that for all of the variables. I did that to make everything qualitative so I could demonstrate the important feature in Uniwin of being able to handle qualitative factors. Okay. Well, let me go into Uniwin just briefly and show you how nicely all this works. So for the moment, I'm going to get out of my PowerPoint presentation. I'm going to minimize that. I'm going to leave Statgraphics Centurion. And now I'm going to find the icon for Uniwin Plus. Here it is. Okay, now, since Sigma Plus is located in France, you will see the menus and the output being in French. Even though I don't speak French, though, I have had no problem at all working my way around. So many mathematical terms are similar in English and French. I don't think you'll find it very difficult to use. The first thing I want to do, though, is I want to open up the data file I've saved. And the data file I've saved is called US Data for Uniwin. So let's open up that file. Okay, there it is. You see each of the states. You see the election column, major farm product column, urban percentage, population density, and so forth. To do a cluster analysis on these variables, I'll look for the dendrogram on the toolbar. There it is. And it says hierarchical classification. All right, let's push that button. It'll come up with a dialog box. The first thing it wants to know is what variables I want to use to classify the observations. And I'm going to choose everything from major farm product down to poverty rate. How do you want to label it? I want to label it by state. I also need to look down at the radio buttons and tell it that the rows of my data table are qualitative, not quantitative. I can then press OK. It's going to ask me where it should save the results. I'll take the defaults. Can I replace the file with the same name? Yes, I can. And what it's done here is done a cluster analysis. Now, the most interesting thing to look at is to look at the graphs and look at a vertical dendrogram. The vertical dendrogram here shows that this particular procedure, and I think it's Ward's procedure that's used by default here, has divided the states up into what appear to be, to me, three natural groupings. There's a natural grouping here, here, and here. Now, this is grouped based upon the same 7 variables that I found earlier to be important, however coded now as 1, 2, 3, or 4, depending on what category they're in, but also something I haven't done, which was the farm product. So we've now been able to introduce into our classification in Uniwin Plus a qualitative factor in addition to the quantitative factors. If you're interested, incidentally, in how this worked out on my map, let me show you what the map is of the Uniwin clusters. It's similar to the maps we were seeing before, except now, of course, we have only 3 groups instead of 4 groups. You can see, though, the western states and the southwestern states are together. The south is pretty much intact except for Georgia. And now the northeast and the north central are pretty much, with Florida and Virginia, define a 3rd group. Okay. Now, another thing that Uniwin can do, go back to Uniwin for a moment, is to do a classification. There are 3 buttons on the toolbar that will do a classification. The first one is the discriminant analysis that we performed before. The second is a Bayesian discriminant analysis, similar to what I did with the neural networks. The third is a discriminant analysis for qualitative factors. That's the one Statgraphics Centurion does not have. All right, let's tell it we'll quit the current procedure, and let's put in the input now for the discriminant analysis procedure. And what I'm going to do is I'm going to put in, as the explanatory factors, everything from major farm product down to and including poverty rate. There are 1, 2, 3, 4, 5, 6, 7, 8 predictors. The classification factor is election 2012. The labels for the individuals are state. Okay. Let's push OK. Again, it wants to save the results. Can I replace the file? Yes. And it now opens up its analysis window. And if I go here now and ask for the classification report, you'll see that it actually did a really, really good job. It got 98% of the states right. In fact, all 24 states that voted for Romney, it classified as being Romney. Of the 26 states that voted for Obama, it classified 25 properly. If you're curious about what Uniwin missed when it did the classification, the only state it missed, it wrongly classified, was Nevada. And in fact, Nevada was the only cattle state that voted for Obama. And that may well be the reason that it wrongly classified it. All the other cattle states, Texas, Oklahoma, Wyoming, Colorado, those sorts of states, they all, well, maybe not Colorado, but Wyoming, Montana, Texas, Oklahoma, all the cattle states went for Romney. Okay. So if you'd like to do either a cluster analysis and or a classification analysis, and you have qualitative factors in addition to the quantitative ones, you can handle both, Uniwin Plus is a good place to look. Okay, that's the end of my webinar. If you would like more information about either of the products I've showed you, you can go to either statgraphics.com to take a look at Statgraphics Centurion, or if you want to look at Uniwin Plus, go either to statgraphics.fr or sigmaplus.fr. As usual, we welcome emails telling us what you liked, what you didn't like, any questions you might have about what I talked about today. They can be sent to info@statgraphics.com. And finally, Statgraphics is on Facebook, LinkedIn, and Twitter. If you'd like to follow what we're doing, we're making more and more use of those social networking sites to share information, to notify people about upcoming webinars and that sort of thing. All right. Now, the last thing I typically do at the end of the webinars, of course, is to take some questions. I don't actually see yet any questions sent in. We did, though, actually, yes, last week have a question. While I'm waiting for you to type in any other questions that you have, there was a question on, well, not last week, last month's webinar, about using principal components analysis on time series data. And I promised I'd do a little bit of research to see how one might apply principal components analysis to time series. Well, I found out really quickly that it's very widely used in analyzing time series data. There's actually a very good example that I found in a book called Analysis of Financial Time Series, 2nd edition. I won't try to say the author's name, because I'll probably pronounce it wrong. You can see it on the screen. In Chapter 9, he shows a very interesting principal components analysis that he performed on monthly returns for 5 different stocks over a 10-year period. He looked at IBM, Hewlett-Packard, Intel, Merrill Lynch, and Morgan Stanley. Good, I remembered what they were. And basically took monthly data over a 10-year period, that's 120 observations of each of those securities, each of those stocks at the same points in time, computed a correlation matrix, and did a principal components analysis on the correlation matrix. And what he found is that there were 2 important components, 2 significant components that those 5 stocks shared. One was a general market component. It was a general trend over time, which was basically, I believe, up over that 10-year period. And all the stocks benefited by that general market component. There was a second market component, though, that contrasted the industrial stocks, IBM, Hewlett-Packard, and Intel, with the financial stocks, with Merrill Lynch and Morgan Stanley. To me, that was quite interesting. There was a difference of behavior between the industrial stocks and the financial stocks. But beyond that, there was not a significant difference in how those stocks behaved over time. There are lots and lots of other examples out there on the internet of how you can use a principal components analysis on time series data. I thought, though, that those of you who are interested in looking at financial data might find that quite an interesting example. And you can just do a Google search and you'll come up with, just look for analysis of financial time series, PCA. It'll lead you right to Chapter 9 of that particular book. Okay. Any other questions? I don't see any other questions coming through. Craig, have you seen any questions?
No.
Gerhard,
no questions.
Feeling the questions today.
No questions.
No questions. Okay, well, either you understood everything or you didn't understand anything. Hopefully it was the former. We will be posting this webinar on our website. Just go to statgraphics.com, look on the menu for webinars, probably later this afternoon. If you want to hear me again, you're welcome to view this again. Or if you have colleagues that you think might be interested in what we talked about today, please point them to our webinars page. I'll be doing another webinar sometime in January, probably a third part of our multivariate methods examination, because there are still some other multivariate procedures that I really haven't had time to talk about. I'll decide, though, between now and January what the best use of our time is going to be. So I thank you all for sticking around. Any questions that you have that you'd rather send us via email, please do. We'll be happy to answer those. So long. Have a good holiday, Merry Christmas, and so forth. Until I see you again, Happy Hanukkah, or whatever you celebrate between now and January.